Hello, everyone. Thank you for joining us for today's Deeper Talk seminar. Before introducing our seminar speakers, a few housekeeping announcements. Today's event is both in person and online. For those online, please use the Q&A button throughout the presentation, and we'll gather those and we'll answer questions at the end of the presentation. At that time, you can also raise your hand in Zoom, or if you're a person, we'll call on you in the room. If you're on Zoom, we'll unmute you so you can ask your question verbally. Along with all previous Deeper Talks, this talk will be recorded and available online at the institute.surf/Deeper Talks, as well as on our YouTube and Vimeo channels. If you wish to receive a notification for upcoming events, please go to institute.surf, contact us. Now it's my privilege to introduce today's speakers. Bryce Pietzyk has held several roles involving underground operations and engineering at the Sanford Underground Research Facility. For over 17 years, he is currently the Director of Underground Operations. His primary responsibilities currently include managing ventilation systems, water inflow controls, ground control, project management, and managing the underground mitigation crew. Bryce is originally from Eagle, Nebraska, and obtained a bachelor's and master's degrees in mining engineering from South Dakota Mines. He is also a professional mining engineer registered in South Dakota and Nebraska. Prior to working at SURF, Bryce worked in engineering supervision capacities at underground trona, salt, and limestone operations. Jason Connot is an underground operations engineer at SURF, has been with the organization since 2019 after working in mining industry in various roles, both underground and open pit mining. Jason is SURF's expert on underground ventilation and maintains the ventilation model that's used to help plan for future operations, develop expansion of underground facilities. Jason also helps assist the underground operations department manage water inflows, ground control, and various projects underground. Works closely with the underground mitigation crew and helps support the diligent work required to keep the underground safe and accessible. Jason has a bachelor's degree in mining engineering from South Dakota Mines and is currently pursuing a master's degree. Jason enjoys being a mentor and has helped create ventilation games for elementary and middle school students. Let's go ahead and learn about maintaining laboratory operations beyond the 4850-foot level. I'll turn it over to Bryce and Jason.
Thanks, Jared. Yeah, my name is Bryce Pietzyk. Jason's right here. We're responsible for underground mitigation crew and everything Jared just said, working with all things underground. Usually you'll find us down there instead of up here giving presentations, but here we are. We'll get started. We're going to talk about a variety of subjects today, starting out with level inspections, and then also talk about water inflow controls that we deal a lot with, and just a few other projects and experiments that we deal with. Jason's going to predominantly talk about underground ventilation. Okay, we're going to start out with the underground level inspection program. So I think most people are familiar with our facility in general, that we are the former home state mine. There are miles and miles of drifts, ramps, raises, shafts, and things that we have to maintain and inspect. We have our footprint limited down to certain areas that we focus on maintaining, whether it's for science and areas of controls that we have to maintain for water ventilation. So if you look here on the right is just nice and that the metric or Vulcan model showing all the bunch of the workings underground. So we don't maintain all that, but we have to have a presence there inspected for safety reasons and just continue to upgrade our infrastructure. So we have a program, we hit all these areas that we can safely once per year at a minimum, sometimes more. And what are we doing? I'm looking at the whole slide here. We're looking for change. We're looking for infrastructure that might need to be addressed. So we look at these areas. We have a system where we go through to specific areas, check on them, look for changes year after year, and then we'll prioritize and maintain those areas as needed. So I'll just go through some examples. If you look at the map down here, this is a plan view of the 800 level. And if you look at the arrow here, it's just one example of many areas that we go look at. On the map here, you also show the gate shaft and the raw shaft to get perspective. We're looking at close to 5,000 feet as the crow flies, pretty much to that area from either one of the shafts, roughly. So it's a long ways back. This area in particular, no concern or anything, but this is the type of thing we observe. This is a wall from the home state mining hand stack back that they used back in those days. And no changes, nothing concerned, but it's something that we look at. And a big part of this too is we want to continue this on. So for years to come, as other people join in this program to inspect these areas, we can pass that information along. So we have years and years of documentation on this. So I'm just gonna go through a few examples of this, things like this. If you look at the 800 level back here, this is actually to the side of the open cut. If you look, those in the room, if you look back past the B&M #2 head frame, it's right or just past that area. And this is another area we're looking at water inflow controls. This is an old foundation here for a door, and this is just an example of the inspection team at the time of this picture where we went back and looked for changes, looking at ground control, looking at water, trying to reduce leakage from ventilation to our system. And I was like, this picture here is on the 800 level, directly below the open cut. So, one wouldn't expect to see ice or anything way back down there, but it just shows you how close the interface on the bottom of the open cut is to old workings. And right here, this area we check, we want to make sure there's not much water. We have no business really going back to areas for science or anything else, but we just want to make sure there's anything that we need to mitigate. If there's anything we need to mitigate, ventilation wise, or sealing off areas, we check on that. So this here is the 800 level, and what we have here, this is an area that we use for, we've stored materials here in the past, and right now we're not using it for anything, but it's an area that we look at and maintain. We have had some geology groups go up and even look at the unique folding up in these areas. And this is an area that is open for science that we regularly maintain for that and could be available for other experiments at some point. I like this one here too. This is the 800 level. Back in the Melinda Ridge route, this is the old workings. Again, ERT team does a lot of training up in this area. We designated for them to train. There's a lot of unique infrastructure in there to do a lot of scenarios with. What I like about this, if you look at the initials, the graffiti on the right side, it says 1/1/2004 or 04. That's actually 1904. That's from old carbide lamp. The miners doing that, and it's more modern graffiti almost 100 years later in that spot. So it just tells you how old some of this infrastructure is. And if you look at, we call that on the right the goat trail. It's kind of a neat area. A lot of history there for probably for a different presentation. And this is 800 level. Captain Powder magazine. We have had some experiments in these areas at one point. And again, it's areas if you don't inspect them, how do you know if there's any change? That's why we're there. And moving down 1100 level, B&M #1. This is the shaft that was former homestay shaft that's now bottom of the open cut. This is where I'm going to get into the theme of water inflow controls. This is one of the first places we capture water. Specifically, I'm not going to switch details. Water comes into the structure, goes over to the sump wall, ends up in the system, either some pipes or ditches to start to get into place where we control. Common theme I'm going to talk about here in a little bit. Critical piece of structure that we have to look at. And if you look at 1100 level pump room, further back, this is B&M #2. This is actually right below that head frame on the 1100 level. Below this is a sump, and this is where Homestay used to pump water from on this level. At some point, we would love to pump water from this level again too, but this is direct capture for our water and areas we have to inspect. And This is on the 1550 level. This is after if we get large rain events. We will go inspect certain areas and make sure it's clean. So this is on the 1550 level, being on number 1. Usually there's not this much water running down it. We go look for that. You know, we know what that looks like from years of experience watching this stuff. If we don't see water there after a big rain event, it means to move somewhere else. Nothing's changed in all the years I've been here, but that's the areas that we have to look at as an example. And another area, 2000 level, this is the Milton Winds hoist room. And another area to inspect for ventilation, water inflow controls. Just adjacent to this is where our water inflow system runs. I like putting this thing up there, just show some of the old infrastructure. What a winds is, for those that don't know, it's basically a shaft that starts underground and stays underground. So this here starts on the 2000 level, ends up on the 3500 level. So this is one we watch. We have no infrastructure. The hoist room here, the hoist that used to be here is actually now down at the old Four Winds area on the 48 to 50 level. And just another example on 17 or on the 4850 level, 17 ledge, the dune for reference, raw shafts here, gauge shafts here, and the dune experiments right here. But you see how much of a footprint we have. Jason's gonna talk a lot more about ventilation, but we have lots of interfaces we have to work with for ventilation, areas we have to inspect, we might not see in the standard brochure for Stanford. And that's an example of 4 winds. I think that might be here. Anyways. All right, moving on. This here, if you want to hit play on this, just an example. If we haven't been on the ground, we're doing these inspections. This is the RAM system, 7 ledge between 1700 and 2000 level. We have side by side. Below this right now, we'll be drive back and forth, and we'll look at maintaining the structure, do our inspections. Okay, let's talk about water inflows. So behind us here is the open cut. We have done a lot of work working with consultants and working with ex-homestay folks just to learn the system, how this works. So imagine if you have a big rain event, water goes directly in the open cut. There's about 250 acres total of catchment area, and split about in half between direct and run on. So if we get big rain events, we can't pump that water from a close enough level before it comes down. So we have a system where we capture that water, direct it to a place where we can safely pump it. And if you look here on the top right, this just shows all the different workings associated with it. So we need to capture that water, move it, pump it, treat it. And we'll go through the numbers here, but the bottom line is there's lots of ways to find 100-year rain events, but this just shows some of the work that's been done in the past to calculate how many millions of gallons during large rain events there is. So you could say it's on your own, but bottom line is, a 2-inch rain, millions of gallons just on that, which we control. So our strategy, just like I said, we divert the water to a place where we can safely pump it out. If you look at the cross section here, you can see the open cut at the top. Okay, right here, and then just from a visual standpoint, just imagine this: water needs to get from here to the pool or a pump room. What we've done, we had a project we did, actually been quite a few years now, where we don't want the water to go through here. We'd rather come up here to a place where we can control it, specifically the 2000 level. And there's several advantages to that. Controlling up higher means there's less whole infrastructure to go through. Second part of it is we save money by pumping it from up higher. And we have flexibility. If we need, right now we're doing work on a pump room, so we have flexibility. We can move water from one spot to another and work through the system. So this is the deep pool. At the time of this drawing is at 5750 level. We don't want this water to get to the 5000 level. We want to keep about 1 year's worth of freeboard underneath below those levels, so that if we have pumping issues or anything else, if we need to upgrade our infrastructure, we can do that. And so right here, we came up with a project and a plan that we executed on 1850, where we capture water through legacy. We can use as many of the legacy homestay controls that we can. And then we put a new raising here. And we could take water to the pump rooms or channel flow it to 5 shaft and down. You know, ideally, we pump as much water as we can from here. We're roughly around 200 gallons per minute, which in reality, home state, the mine itself or our facility now, base loads are only 750 gallons a minute. We're a pretty dry mine when you look at just the size of the infrastructure. When we get large rain events, you can easily get thousands of gallons a minute into the system. That's what this was designed for, is to capture that. And just another drawing this for more of a better graphic. If you look at plan view in the 2000s, so the project I'm talking about, we put a new raise in, which is basically just called a new borehole, 40 inches wide from the 1700 down to the 2000 level, and from there, that's where we installed a collar, and we put 20-inch HDPE pipe all the way through here. So we had to go uphill to get to 5 shaft, and then we run that water through 20-inch HDPE pipe to this location, past the Honda shaft. We don't want the water going down the Honda shaft here either, to a concrete wall, and then channel flow it to 5 shaft. Majority of the time, though, we only do that a few times of the year. Most time we're sinking raw shaft down to the pump rooms. So a little bit about that project. This is an example of us backing back up. We've got 40-inch line and HDPE pipe coming in. You've probably heard a lot about the shafts here. Everything has to go down the shafts to get somewhere. We actually, it's most people, when they put a pipeline in, they're not putting it 10-foot sticks at 20-inch diameter, but that worked out for us. We put it down and we use a local contractor to fuse all that pipe together. Been working good. Other stuff, let's talk a little more about the crews related to this. Crews that work for Jason and I, actually, we do a lot of this work in-house. One example of this is working with the engineering department for installing walls. When I started here in 2008, I think it was roughly about 2009, we had a project. We identified that working with past home state miners and other people familiar, we need to put walls up to help protect the infrastructure. So we did that, and we used timber. We had a designer, we did that. Well, several years later, now they need replaced. So recently, within the last 4 years, we went through and prioritized these and picked out the ones we need to and replace the concrete. So the nice thing is, funding wise, we're able to replace timber with concrete and really upgrade our facility. And this is an after picture. This is nice seeing something clean and like concrete and new in the facility and structures like this. So then on top of it, Jason will talk more about ventilation. We use a product. Just some metal panels that we use to control ventilation. And it's just pictures, Jason back there doing ventilation inspection on these areas. Other stuff these crews work with. Just briefly, I know you probably heard a lot about the Sigma V project, the site on the 4100 level. Our crews help manage that, working with contractors and our scientists to put this project together. This location next to the gate shaft. So on this project in particular, not too far from the gates, we actually had to build a wall here. And then we brought a contractor in to blast the new alcove out. And to put this experiment in, I won't talk much about, Jared can answer questions about the experiment if he wants. And then just a few pictures of that. So we protected the shaft. We don't want any blasting to affect the shaft. Had a contractor in, do this. Crews that work for us actually remove the material or muck, we call it, and put it on the spot on the 4100. And then the experiment was able to contract in a driller to come in and drill this project down. Just one example there. And then that's what it looks like when it's done. So it's nice seeing these old spaces turn into something new, and how we upgrade these facilities. If you look on top of it, ground control wise, our crews put in all new ground support, modern technology. So there's always some sort of ground support above your head. Pour new concrete, put rock down, and got everything all lit up. So we got nice space for people to work, because we want all our customers and stakeholders to feel comfortable in the spaces that they're at. And just one more example before I go to Jason. There's a project, or we have a partner on 1700 level that's put a lot of upgrades into our facility also. We work with them. They outfitted their space so they can do project demonstrations on of their items, and then upgrading rail is another thing that between us and other contractors we have done. Over time, rail, that, as you can imagine, ties get rotten, rail, the steel, it'll rust. Putting this in and then coming back later, putting ballast in, just trying to upgrade all this facility. So it's a quick overview of some of the stuff we're working on. Move on to Jason. Thank you, you're next.
All right, good morning, everyone. My name is Jason Connot. I work with Bryce as the underground operations engineer here, and we're going to talk about my favorite topic, underground ventilation today, and kind of how we plan it here at SURF. So I'm going to ask the group, why is ventilation important underground? Can anyone answer? No one? Good. Safety underground, personnel. Equipment. It needs that to work efficiently. Also, just the overall operation of the underground itself. Increase worker productivity underground. So if you're working in a hot environment, you're not going to get a lot done. Where you're working in more like a 65, 70 degree weather, you're going to get more done, you're going to be more productive underground. So what does it impact underground? Everything. Ventilation impacts everything underground. So just a quick overview of our ventilation system here at SURF. We have 2 intake shafts, the Yates and the Ross, which are color coded in the blue there, and then 2 exhaust shafts. The Oro Hondo is our primary, which is in the middle, and then number 5 shaft, which is on the far right here. Air flows down about 320 combined to the 4850 level, 320,000 CFM. We're exhausting about 500,000 out the Oro Hondo. So that other airflow that we're missing is typically going to that 1700 to the cat lab, 17 ledge, and throughout the middle workings of our system. So how do we plan what we need for underground ventilation? Well, we use a zero-based design system where we're going through the diesel horsepower, the science requirements such as HVAC systems. We're excavating like we have in the past, where you've got regulations for that. We also supply air for our pump rooms, electrical substations. We want to provide ventilation for our main travel ways such as 17, 4100. People aren't always there, but when they do go, we want to have it ventilated properly. As well as the leakage coming into our system. We want to account for that. How do we control that? As well as provide some sort of contingency if something needs to be adapted, we have that capability. So we go through this little chart here. We break down our horsepower diesel equipment, which seems kind of light at 86, and I'm going to go through that here in this next slide. Contractor diesel horsepower. This was actually just a year ago with Tyson mining when they were doing our bypass drift and kind of finishing up in the caverns. Underground personnel, we account for our max at 250 personnel. The different headings at 3 that we had it for the north, south, and central utility cabins at 3 feet per minute at the different areas, as well as our bypass drift excavations. And then we go to the pump room substations. We want to supply about 5,000 CFM to cool those down, keeping them in efficiently operating. And then our total science requirements that we have currently, which is pretty much the Davis and Ross campus. And then we throw a contingency of 10% in there. So last year we were at about 427,000 CFM needed, and we can produce about 500,000 with the Oro Hondo system. So going back to that horsepower, this is just one page of our equipment underground. You can see the column kind of right in the middle here. This is the fully rated capacity of each one of those pieces of equipment. If you supply 100 CFM per brake horsepower, we can never meet the overall requirement for that ventilation system. So what we do, we go through and we assign a usage, a utilization factor, where we give it a percent time that it's going to be up and running. No piece of equipment underground is going to run 100% of the time. So that's where that comes into play. And then we can break down that what rated horsepower is being used throughout the year and give it a better number with the CFM requirement. So that's where we got that 86 diesel horsepower for our equipment. So that's kind of a high overview of how we plan. But when I first started and we were doing that, it didn't really make sense to me because there's high physics experiments that need to know what ventilation requirements were needed. So I came in, we created this ventilation assessment report where we talk about where the intakes are, where the exhaust routes go to for each one of these levels. We talked about Davis, the Ross, LB&F, the 1700 cat, the 4100, different substations, and we go through the leakage routes, the detailed description of each one of those pathways from the intake to the exhaust and how it feeds into other levels and other areas underground. And then the key ventilation controls of that area. And then we further break it down, kind of like how we do the zero base plan, but for each lab space or area underground that we go through. And again, we use that utilization factor there for each, and then we make a map of where those requirements are, so we know what we're hitting, what we need to do. So how do we know that we're hitting these requirements underground with our ventilation? Well, we go through and do field surveys underground. So this is one that we do out of 13 primary levels on the 3950. We have ventilation maps that correlate with each ventilation station underground. It's kind of hard to see on this presentation, but there's 39 Ds, a number which correlates to the point here, where you are on that description, the time we're taking it, the temperature, the barometric pressure, the humidity, the velocity. We calculate the CFM at that location, so we know what we're providing underground. It's kind of a health check for our ventilation system in its whole. We also go through and get the key door ventilation controls underground, which you can see in this section here. Pressures, what position they were in when we were doing the survey, so we know when we go to do our ventilation model, which what we use is VentSim, and how we correlate that, the actual field surveys to this model to make it more accurate. Up in this upper right corner is the LB&F caverns that we've been modeling with them. This middle picture is actually the entire system. This little green dot is that. So you can see we have a huge ventilation system here at CERT. And this is kind of everything just broken down into the areas that we have modeled currently, which is roughly about 5,000 airways in the VentSim model, which is quite large. In this video here, this was actually done with Kiewit when they were doing the pilot drift excavation, and everything in blue is showing good, clean air. This is during a blast, and everything at light pink is showing blast gas. So we're showing them how we design our systems, the negative pressure system in this case, where it's going to go, who's it going to affect. In this instance, we actually closed off certain levels up above us, restricting access so no one would get in that vent stream and get blasted with blast gas. So you can kind of see how it's going through our whole entire ventilation system, which is very cool. How fast it actually evacuated the phase there, which is about 4 minutes. You can see the clock. Very useful tool for us. We can also do diesel particulate matter, have activity tracks throughout a level, assign a DPM rate out of that equipment, and give us a better understanding of what we're providing. How safe is it underground? Do we need to do something else to make it better? So we can't always be underground taking surveys. So we're starting to implement a ventilation monitoring system called Maestro Digital Mine, where we have them stationed in unique areas of our intake and exhaust shaft, exhaust pathways. And we can see different gases that we put to these units, such as CO, CO2, O2, NO2, the airflow rates at each one of those locations, as well as humidity, temperature, barometric pressure. And if anything happens, we can also see the adverse changes through a trending system, which is on the bottom right here. We can kind of go back and correlate those key air door changes and how they respond to our ventilation system with this ventilation monitoring. So we also do maintenance underground. There's a lot of infrastructure, as Bryce was saying, with walls. We've gone through and updated some of the legacy air doors to these penny stoppings. This one was actually on the 3,500 level right before the Honda, which was helping LBNF. We actually picked up about 35,000 CFM on the 48 by installing this wall. Another example of that is on the 31 exhaust on the 4,100 level. The picture on the left was actually after a blast on our bypass direct excavation. When we closed the blast doors, the fan was still on, which pulled this wall apart pretty much, which short circuited their exhaust system. So we had to go in, determine what the cause was, found that, and then installed a new one, kind of reinforced it so it wouldn't happen again. And we've also been doing upgrades to our ventilation system, which is doing these pneumatic doors, which is on the 4,100. Mostly to keep people out of harm's way. These doors can have a lot of pressure. It can be very dangerous by opening manually. So we want to keep installing these, incorporating these into our design, where the high pressures are, and keep people out of harm. Another thing is the ability to control ventilation without manually going down. So this is an automated regulator that we installed in the Honda shaft from 2000 level. We can actually close this all the way, push air down to 3950, 4850, or we can open it up and control the airflow for the cat lab on 1700 with this one regulator. We're looking at installing one more on the 3950, which is actually in progress right now. Hopefully give us a little bit more control of our entire ventilation system. We also do inspections of our ventilation shafts, such as 5 shaft, number 2 air arrays, the Hondo, as well as the 4,700 level overpass. These pictures, I didn't put the video in here just because it took up a little bit more space. But these are pictures of our 5 shaft. We have a plug in there, which represents changes and how we control that airflow. So we want to send the camera down and see if there is change through year to year. Hopefully coming up with a plan to get that unplugged. We're also working on another project on the 3950 where our Hondo shaft has been spalling rock and has filled up past the 3950 level here. So we want to go in, muck that out, provide a more reliable means of ventilation off the 17 ledge through this level. We can also drop our air pressure on the fan, which is going to result in lower operating costs of that unit. That's it. Any questions?
What is that?
Very good. Bryce, Jason, thank you so much for a very interesting presentation. Let's open it up for questions. There we go. You want to unmute Steve and have him ask his question? Steve's from Snow Lab.
Yeah, are you able to hear us? Ruh-roh. Give me one.
Steve, we'll get you.
Yeah, sorry, we had the wrong device selected. Can you hear us now?
No, just give us 2 seconds.
Okay.
We can almost hear you.
Okay.
But your he's gonna ask what your pain was. You better come.
Oh, that's a high-tech piece of ventilation equipment. No, someone gave that to me as a joke.
Try again, Steve.
Can you hear us now?
Yeah, yep, perfect.
Great. So this is Erica at Snow Lab. Thank you for the really interesting talk. I I had a question about the wall that was replaced on slide 28, the timber wall to the concrete. It looked like it was just kind of on the surface of the ground and the ground did not look very sturdy. We wondered if the concrete wall went kind of deeper into the floor of the drift. Yeah, that one.
Yeah, one thing you're talking about the ground around it.
Yes, yeah.
Yeah, the ground, if you look on the left side, what we did, it's a project that we put in where we were there for a short period of time, so we installed brand new ground support over the top of where people were working there. Barred and inspected the ribs in that spot, so when we did that wall, we do these, we'll inspect the area, install proper ground support. And then one time we're coming back, these areas inspecting it, so, you can see there's some legacy homestay ground support in place there. Typically where we do these walls, depending on the assessment we do, we'll typically install new ground support.
But you also hit your in, right?
We did hit you.
Oh, yeah, I guess.
Yeah.
That's where you go with that, yeah, they're hitched in about almost a foot into the ribs, so in the ribs and the sill, so we would dig all that out, go from there. There is structural steel that's in all these walls too, so they've all been designed out.
Thank you.
Yep.
Thanks, Victor. Other questions? Yeah, let me do that. Sorry.
In the inspections you do and all those places that you try to get to at least once a year, do you know the total mileage of drifts that is like accessible in those inspections?
It's a good question. I don't have that number in front of me, but you know, it's lots. I mean, right now, I mean, we're, you know, we say we maintain between 12, actually expanded out around 14, 15 miles that we really maintain. You're easily 100. I think I don't have it with me. I think I calculated that once. That's a good thing. I'll take a note to actually do that. That's an interesting stat. It's miles.
Yeah, when I'm doing presentations with the public, I usually have like 12 miles are maintained. 370 total miles in the history of homestay are kind of my two statistics, but it'd be fun to have that.
Oh, yeah.
Third one in the middle there.
No, it's a good point. We'll call it inspectable areas, you know, on that. So yeah, I'll do that to you.
I think we bumped up the maintained footprint to around 20 miles.
20 is over if you want to be official on that.
Other questions?
So I have to get out of PowerPoint. And chat. All right, question here from Casey Peterson. How much variation do you see in water inflows? What has been the daily high and low and median, if you have that statistic as well, but water inflows, maximum?
Yeah, right now, I don't have it in front of me to give you the specific number, but typically, you know, what we see reporting to the 2000 level, which is where we capture majority of the runoff from the open cut, we're usually around 200 to 300 GPM base loads, and that's where we are, just over 300 right now, with what we've been seeing. But I've seen that thing get pegged out to 3,000 GPM, and we keep an eye on that. We actually have flow meters on that system that we can look. But I get that number to the treatment plant, but we could trend it what we're getting on that. But the system's been effective so far and controlling and also directing where it is. I guess one thing to point out also is even when we get the big rain events, we'll take as much to keep pumping off the 2450 is where that starts to recapture from as we can. But when we can't pump as fast as that comes in, that's when we send it to 5 shaft and down to the pool, keep up with it. But our goal is to always keep up. So. Yep.
Follow up here, how do you handle high pump? How do you handle the high pump longer or have enough storage? So high water inflows, how do you manage those? Pump higher flow?
We pump what we can. We'll do the max we can from our pumping system as we can. The goal is to not put as much in the pool as possible, just because it costs more to pump than that.
Good point. maybe one other thing to tack onto that is in the early days of operations that sort of water inflows would cause us to restrict access underground. And that hasn't been the case with some of these water inflow projects.
Yeah, that's a good point. I mean, really the bottom of the Ellison shaft, which is, 38, 39, 50, that location is, we used to have to restrict access because water would get to those areas and pond up in places that we can't get to in that inspection areas. And, yeah, since this has been in place, we have greatly reduced that.
Yeah, absolutely. Other questions?
We have a few on the Q&A.
In the Q&A, okay, got to pull that up here. Very good. All right, let's go.
Right.
Alrighty, comment here, great presentation, guys. I have a question about the ventilation system. There's a significant difference between the intake and exhaust flow rates. How is the volume of air in the facility being balanced?
Yeah, so that 320,000 CFM that I mentioned before, out of that 500 is directly going to the 4850. So we have other levels that we need to ventilate, such as the 1700 level, the 4100, other levels that we conduct science at. So that's where that difference is.
Very good. Next one here from Tom. Can you address how the emergency response team interacts and prepares with you for ventilation changes?
Yeah, so we are actually implementing a change form where whenever I do a change, we send this out to the different parties of the underground, so they are aware of what's going on. Currently, I just send out an email when I make those changes, send out a map with what's changed, with the actual flow rates underground, the directions that it's going, so everyone's aware. Try to communicate the best I can when we're switching fan speeds, making changes to controls underground.
Very good. Another question here, Tyler Arts, someone that is familiar with our operations here. Any new technology that you guys are using or looking into to assist with inspections, LiDAR, drones, remote vehicles, AI, anything in that?
Yeah, well, it's a good question. There's a lot of new technologies out there. We've seen them at the trade shows. There's drones. We are working, we have worked with quite a few folks from industry and from institutions to look at this. Most recently, a drone from South Dakota State University, who worked with their senior design group, that had a LiDAR scanner on it too. Right now with our inspections, we cover a lot of ground when we do these. We're doing mostly photograph now. But we're always eager to see what else is out there as technologies advance. I think you mentioned. Yeah,
I think we marked that one off. There have been some experiment groups, even some senior design projects testing drone technology as well. Another one here from Snow Lab. Anything done to treat the water or the air that's pumped out? Contaminants such as carbon monoxide, hydrogen sulfide, that would be mostly for the ventilation.
No, we do not treat the exhaust air stream.
yeah.
Certainly the water,
Yeah.
certainly the water goes through a water treatment process that we operate on the surface. Quite a few steps in that water treatment. So the water definitely yes, air is also no.
We don't really have a whole lot of contaminants in our underground ventilation, so there's no need to treat it. I should add it.
All right, another one here from Casey Peterson. In the drift called Millenville, not sure the name or spelling, the floor appeared, oh, that might be the Millennium. Appeared to be very narrow. Why was it configured that way?
Yeah, so that's really old working. So there's quite a history there. So that was its own mine that Homestake actually eventually bought out and broke into. And they were following just a practice of following a vein through there. And the wider it is, the more waste rock they're taking with it too. And
Did I pass it
oh,
back the other way?
I think we got two more this way.
There we go.
Right, oh yeah, this one's referred to here. So they're only gonna take what they need at that point as much as possible. There were not mechanized mining methods back in those days. This is really old, so they were moving stuff by hand, maybe mule even. So it's really old stuff. That's what's cool about it, but they're not gonna go into like a mechanized type mining method where you're mining a lot more, doing a lot more development. So they're gonna do as little as possible.
Other questions? Anyone in the room? Actually, I have one question for Jason. You mentioned current max, maybe 500,000 cubic feet per minute. If we make some changes to 5 shaft, what's the theoretical maximum?
We could probably pull another 500,000.
Oh, wow.
See if then.
Up to 1 million.
Yep.
Is that what Homestake did in production?
They were doing like 3 million if I remember.
They're exact.
Oh, no. Wow, that's impressive. Any other questions? Any last takes before we sign off? Oh, there we go. Perfect. All right. I imagine the ventilation here picks up some heat. Yes, it does. From the surrounding rock by the time it reaches the 4850 foot level. Does the air need to be conditioned at any point in this system?
For the experiments, yes, we do have chillers underground that supply that cooler air for that space. As far as sending it down from the surface to 4850, we do not. Certain times of the year, like right now, we actually open up the 300 level. We pull air across that down the shaft. So we're utilizing that cooler rock temperature, pull the air across it to cool the air down, to go down all the way down to 4850. We typically see about a 5-degree difference when we do that. So
What about the winter time?
yeah, the winter time we close that off.
What about,
We use the shaft heaters. Yeah. So we close the 300 portal off in the fall. And if it gets below 35 degrees, I think is when the heaters kick on for us. So we don't freeze the shafts out. We've got a lot of infrastructure, water, air, everything goes down. So we don't want those freezing.
I know some mines pull their air across permafrost or frozen lakes.
Yep.
Similar to the 300 example that you provided. All right, one more question here. What are some of the safety systems in place or in design to deal with oxygen deficiency hazard associated with some of the science experiments?
So some of our engineers do the calculations for us, as well as consultants coming in to design the HVAC system. And then we maintain the air going across those HVAC systems and sensors placed throughout the Davis, I believe. So we do monitor that airflow, CO, oxygen sensors. So we just monitor, I guess.
And there's a design quantity of air that we require to bring across that. That's what we do.
And that's where that ventilation assessment report comes into play for us. We know those requirements, we know we've got to supply. And do the field service to ensure that it's possible.
Yeah.
we also have controls, if those monitors pick up ODH hazards, they can actually turn parts off. So that we don't introduce more ODH hazards.
Yeah, the HVAC system can be modified to compensate for that in different zones. And that ODH calculation process involves quantitatively analyzing failure rates. The fresh air source is a critical part of that as well. How are we doing on time? One more question. Hey, Casey, your last. What is the volume? What volume was flowing during the smudging, recent smudging by Marty Two Bowls Jr.?
We had about 160,000 CFM flowing down the roads at that time.
Good. All right. Well, very good. Thank you again for obviously an engaging presentation. We had tons of questions. Just to wrap up, this talk will be available to share and view on YouTube, Vimeo, and at institute.surf/Deeper Talks, our web page for this event. Next month's Deeper Talks will be on June 11th, same time, 9 a.m. Mountain, and the topic will be dark matter with featured speaker from the Center for Theoretical Underground Physics and other areas set up. As always, your feedback is important to improve the program, and we appreciate any suggestions for speakers, topics, or future talks. Please fill out a short survey that you'll receive immediately following the talk. It'll be on Zoom and in your email. Once again, thank you very much, and we'll talk again next time.